By 2050, we're on track to have 10 billion people on our planet. Since agriculture already uses half of our vegetated land, it is important to improve the crop yield to produce more food within the same or less area. This can be accomplished by identifying and growing the best possible seeds to optimize yield. Therefore, this research utilizes genotypic markers and environmental data, aiming to address the imminent food challenges that humanity is expected to face in the upcoming decades. In this research, we have three main data types: phenotypic values, genotypic markers, and environmental features. For phenotypic values, we have 13 columns. For genotypic markers, we have approximately 3,000 columns. And for environmental features, we have approximately 60 columns. For genotypic markers, we have three values: 1, 0, and -1. 1 is for homozygous dominant, 0 is heterozygous, and -1 is homozygous recessive. We have in total 1.1 million rows, and we have year from 2000 to 2008. For the data processing, since we try to predict yield based on the genotypic markers and environmental features, we drop the rows with NAM value yield, and we fill out 0 to the other NAM values.
After imputing the data, the next step was to pick our models. We tried several different approaches ranging from tree-based models to neural networks to support vector machines, but we finally narrowed down on tree-based models. Among tree-based models, we narrowed down to three. These were XGBoost, LightGBM, and Random Forest. All of these are different gradient boosting or ensemble methods which are based on decision trees and offer robustness, accuracy, speed, and even can be used for classification and ranking tasks. For this, the metrics we chose were R squared, which is a statistical measure, represents the proportion of variance. The higher the variance, the greater the explanatory power of the model. We also used MAPE, which is the mean absolute percentage error, which represents the mean absolute error as a percentage, and that was useful for relative benchmarking between the models. Looking at the results, we did two types of experiments: one where we ran it within the same year, and one within different years. Within the same year, when we fed genetic markers and genetic plus environment, we saw that XGBoost performed the best. However, when we compared year to year and we fed genetics plus environment, LightGBM performed the best with 2000 to 2007 as train and 2008 as test. For the future goals of the project, we want to explore hyperparameter tuning and dimensionality reduction, other data imputation methods, and statistical methods like mixed models and linear mixed models.